So today I would like to discuss two things. One is chlorine and NaOH production from the salt solution and cement production. If time permits, I will also talk about pharmaceutical production processes. So in the after mid 19th century, chloralkali process is the popular one to produce chlorine and sodium hydroxide. Before this chloralkali process, to produce chlorine in the beginning of 19th century, hydrochloric acid, they used to produce chlorine from the hydrochloric acid with MnO2. However, the yield was very low. Yield was very low for this reaction. The mid 19th century, Decon process, a popular Decon process, that is catalytic oxidation of HCl to produce chlorine. After invention of this process, it became very popular as the yield is almost doubled. But in this process, we use catalysts. At the same time, in the mid 19th century, electrolysis of salt water was also developed or invented. And it started implementing at the end of 19th century. Although it invented in mid 19th century, but the commercial implementation started at the end of 19th century. And there are many industries now to produce chlorine gas and NaOH from the salt solution. It's a simple electrochemical process, that is electrolysis of salt water. So in this electrolysis process, sodium chloride and water reacts and produces NaOH, H2 and Cl2. This is the overall reaction, but the major reactions which I will show you in the next slide. So what is this electrolysis process? If you take an electrolyte which contains positive ions and negative ions, we have a beaker. We have a beaker. In this, we have an electrolyte which has ions. So whenever you dissolve any salts like sodium chloride, or magnesium chloride, or calcium chloride, whatever, as soon as you dissolve the salts, what will happen is the salts upon dissolving, they'll be split into individual ions. Suppose if you dissolve NaCl, you will have Na plus ions and Cl minus ions in the water. So if you put two electrodes, electrodes could be any conductive material, electrically conductive material, graphite, titanium, or platinum coated titanium, whatever conductive material, electrically conductive material could be used as a electrodes here. If you connect these electrodes to a power source and if you give sufficient amount of electrical energy input, one of the this conductive material which is negatively charged will act as a cathode, and the positively charged conductive material act as an anode. And anode will have positive charge and cathode will have the negative charge. Because of this charge difference, because of, see, this is negatively charged whole material and this is the positively charged whole material. Because of this charge difference, naturally positively charged ions attracted towards the cathode and negatively charged ions attracted towards the anode. Now, some of the molecules, or some of the ions can undergo through reduction reaction. Some ions can undergo through oxidation reaction. Some other ions can go through oxidation reaction. So, if you take a context of sodium chloride in water, that is the right hand side picture. So, if you dissolve NaCl in water, the NaCl will be turned into Na plus ions and Cl minus ions. And NaCl is dissolved in water, so it will contain water also. So water, Na plus ions and Cl minus ions. These are all the present. You have placed a conductive materials. It could be graphite, simple graphite, pencil graphite we can use. And here this is connected to a power source, and if you give sufficient amount of energy, as I said earlier, this will be cathode connected to negative charge and positive charge connected to anode. Now the chlorine Cl minus ions here, the Cl minus ions here, like I said, Cl minus, this is Cl minus ions and Na plus ions will be there. So Cl minus ions migrates towards anode. Na plus ions tend to migrate towards cathode. So this chlorine ions undergoes through the reduction reaction. The chlorine ions undergoes through the reduction reactions. So two chlorine ions join together and forms chlorine gas and releases the electrons. And whatever electrons releases, that will be transferred to the cathode. Whatever electrons releases, that will be transported towards the cathode. So whatever electrons comes here in the cathode, what will happens is reduction reaction, sorry, oxidation reaction happens. Oxidation reaction happens. So water combines with these two electrons, utilizing that will break down to, water will break down to H2, hydrogen gas and OH minus ions. Hydrogen gas and the OH minus ion. So that whatever hydrogen gas which is formed, that will be liberated as in the bubbles. And here whatever chlorine gas formed liberated, that will be bubbled here. This OH minus ions, the reduced the OH minus ions will combine with Na plus ions and forms the NaOH. Forms the NaOH. So somebody did a simple experiment. I just found in the YouTube, and we can quickly, probably you might have seen already such videos, just to demonstrate in a in a quick way. Some So here he just taken salt water and just kept this pencil graphite, like whatever sharpened pencils he kept this immersed in water, and you can see once you apply, once he applies sufficient of energy with help of the battery, and you will observe that a the chlorine gas come from here, and you will also see a little amount of hydrogen gas also will come from this one. This is just salt water. This is just salt water, and this is the pencil, sharpened pencil at the both ends. And since the pencil contains graphite, that will act as an electrode. And if you connect it to a battery, see, you can connect it to a battery. then you can see that a chlorine gas comes out, and we have the hydrogen gas comes out, and we have the NaOH formation in this one. We have the NaOH formation in this one. So this is the simple experiment. Any one of us can do it easily. So you can watch. I'm sure you already know this type of things, but if you're interested, you can watch. I will also keep this YouTube link here. The reason for me to check the YouTube videos just to see whether any reality, like a few weeks back, someone suggested. I think the Shanmugh suggested that it's better to have some visual uh, processors. So I thought better to check some of the available one. Then I got few whatever is available and found out. So what is the issue if I directly do like this? Some of the drawbacks with this direct electrolysis is that some of the drawbacks is that you know we will never be able to achieve 100% conversion of NaCl into NaOH and Cl, chlorine gas and hydrogen gas. Never be possible. Only whatever liquids which is close to this electrodes, they will get be involved in the reaction. So ultimately we end up with NaOH after certain amount of electrolysis process or a certain amount of time, we have NaOH and NaCl. It is very difficult to separate NaOH from the NaCl. Of course, we can do crystallization or thing. We need to separate it. We need an additional process, and it is not so easy to separate this one. Either we have to evaporate it or we have to crystallize it, then we have to remove the NaCl, and it will be an expensive process. And also, the residual NaCl will be always a concentrated one because we reduce some of the NaCl, so remaining NaCl will be a concentrated one. So even if NaOH is formed, there will be purity of the NaOH will be very low. The purity of the NaOH is very low. Now, another important problem also comes here is that although this oxidation reaction happens in the cathode, these Na plus ions can also migrate to the cathode and stick to this one. That will reduces the efficiency of the cathode or the efficiency of this oxidation reaction to be happen. So these are the two major problems. If we directly put two electrodes in a beaker which contains salt water to do this one. So what is the way we can enhance this process? Although this process what I explained so far is invented in mid 19th century, it commercially not implemented because of these two drawbacks. So how did they mitigate these drawbacks? Let us see that one. So there are three types of electrolysis, commercial electrolysis were developed. One is mercury cell electrolysis, another one is diaphragm cell electrolysis, third one is membrane cell electrolysis process. So what is mercury cell electrolysis process? In mercury cell electrolysis process, mercury acts as a liquid cathode. Mercury acts as a liquid cathode. So here in the mercury cell process, we have mercury that is acted as a cathode. So we will have to place an anode here. And for electrolysis process, always we need to give an additional external power supply. We need to give an external power supply. So what happens is that these Na plus ions which are reduced and formed as an amalgam. Formed an amalgam. So this Na plus ions present in the chlorine Cl minus ions move towards the anode, and this reduction reaction happen, and chlorine gas formed, and whatever chlorine gas formed which will be liberated, and here we feed saturated brine solution to this mercury cell. So whatever Na plus ions form, that will be moved towards this mercury, because that is the cathode, and that Na plus ions combines with mercury and forms this amalgam. Forms this amalgam. So now, if once we form the amalgam, we need to separate this Na plus ions. Then only we can recycle the mercury back. Then only we can recycle the mercury back. So what they do, what they found out, that this amalgam, when combines with water, when reacts with water, when amalgam combines with water, reacts with water, that Na plus ions combines with OH hydroxyl ions and forms the NaOH, and this mercury will be separated. The mercury will be separated, and whatever H plus ions are there, that will be combined and formed as a hydrogen gas. Formed as a hydrogen gas. So here you can see whatever amalgam formed from the mercury cell is removed and sent to another column where it reacts with water, H2O, where it reacts with water and forms which separates the mercury and NaOH and hydrogen gas. So whatever mercury which is settled, because this is the high density one, settled, that will be recycled back. That will be recycled back. That will be recycled. So this way we are able to produce chlorine gas, and we are able to produce NaOH, and able to produce hydrogen. Now the NaOH produced here, there is no way contaminated. There is no way contaminated with salt here, because we have taken the dilute salt solution here. We are only taking the amalgam. We are only taking the amalgam which is formed here. So you can get highest purity NaOH using this process. We can get highest purity NaOH using this process, because we are only taking this amalgam and reacted with the water. There is dilute brine is not at all connected to this one. So one can get highest purity NaOH from this mercury cell electrolysis process. But as you can see, always we have to top up, like we have to introduce some more mercury, because there is a possibility of the trace amounts of mercury might be leaving with the streams. So the biggest issue, the biggest problem is, even if very trace amounts of mercury is present, that is extremely dangerous. That is extremely dangerous. So because of this, because of this handling of the mercury, which is very toxic with water or with whatever processing conditions, this is very limited number of industries are made, because severe protocols are extremely tough protocols needs to be followed. So after this mercury cell, they invented and developed diaphragm cell process. The diaphragm cell process. What is the speciality with this diaphragm process is that if you take in a compartment that is separated, or the two electrodes are separated by a porous, microporous diaphragm. Microporous diaphragm. The two electrodes are separated by a microporous diaphragm. So one side we have cathode, another side we have the anode. So anode side we feed saturated brine solution. Anode side we feed saturated brine solution. So here these Na plus ions are there and Cl minus ions are there. In the cathode side, we just feed water. We just feed water. We feed water. So we are not combining electrolyte with water. We are not combining electrolyte with water here. Now we know that the molecule size of chlorine and molecule size of sodium are different. The molecule size of sodium and the molecule size of chlorine are different. So by selectively taking this porous diaphragm membrane, so this membrane supposed to allow only sodium ions through this one. This porous membrane, the pore size is selected such that it will allow Na plus ions. It will allow Na plus ions because of this charge difference. Because of this charge difference. So what happens? This oxidation of reduction of chlorine happens at this anode. The chlorine gas which is formed, which is liberated, and Na plus ions supposed to migrate towards the anode side. And here, whatever once you close this loop, the electrons which is transferred here that will be utilized for the oxidation of water, and that reduces H plus ions and OH minus H2 gas and OH minus ions. That OH minus ions which is formed here in this oxidation reaction will be combined with Na plus ions and forms the NaOH. That is the overall process. But one problem is that because of this, although Na plus ions supposed to migrate towards this one, even if whatever high quality porous membrane, we'll never be able to make always uniform pore size membranes. We'll never be able to make uniform pore size membranes. So because of this concentration gradient, some of the brine solution, NaCl, Cl minus ions also migrates. Some of the Cl minus also migrate. So although they used selectively or proper membranes, but always they found out that this contains NaOH and NaCl. This contains NaOH and NaCl. So although they could mitigate this issue to a certain extent, but they could not completely mitigate the contamination of NaOH with the NaCl. Contamination of NaOH with the NaCl. So asbestos, these microporous diaphragms made of asbestos used to use in this diaphragm cell process. Diaphragm is nothing but a flexible polymeric material, a flexible membrane type of material that separates these cathodes and anodes in this process. So later the most popular process is membrane cell electrolysis process. Membrane cell electrolysis process. What is the speciality with this membrane is that these are the very specific ion exchange membranes. These are the very specific ion exchange membranes. Ion exchange membranes. So there are many polymer molecules. Biopolymer or synthetic polymers. They can be selectively surface functionalized. They can be selectively surface functionalized. So for example, if we take nitrocellulose membrane or any cellulose membrane, nitrocellulose or cellulose membrane. Cellulose membrane. I'm just giving an example. So if you take the cellulose, let's say this is the glucose chain. I'm not. Of course, we can draw a glucose chain like this. You will see that it will have COOOH. Always you will have the hydroxyl groups. So whenever we have these hydroxyl groups present, these are the negatively charged. These are the negatively charged. So if you put some, let's say if I put a cellulose film here, if I put a cellulose film here, and if I put some silver ions, like let's say Ag plus ions, obviously these positive ions will definitely migrate and sit on the surface of this cellulose film. Sit on the surface of this cellulose film. Similarly, in this case, Na plus ions, in the case of salt solution, Na plus ions, if you put such type of negatively charged material, these Na plus ions, because of the opposite charges attracts each other. So Na plus ions will tend to migrate over this film. And suppose if you take uh, any ethylene amine based ethylene polyethylene, if I take polyethylene amine polymer, if you see this polymer chain, this will always have the NH4 plus ions on the surface. NH4 ions on the surface. So there will be multiple these ions on the surface groups. So if I put this polyethylene amine here, no Ag plus ions or Na plus ions will not be attracted. Will not be attracted to this one. It will not be attracted to this one. So this way, I just given only two examples here, but there are so many with the invention of good polymer chemistry. People could completely uh, ion selective surfaces they could able to produce because of this with the presence of catalyst or without catalyst. There are good techniques available to produce this ion selective membrane. So we can make a polymeric membrane that can be fully uh, anionic charged, negative charged, or we can keep a membrane that can be fully positively charged. Both are possible. So here, what happens is that this membrane, what we take in this membrane cell alkalisis process, they are the anionic membranes. There are two types of membranes: ion exchange membranes, cationic membranes, and anionic membranes. So this is fully negatively charged. If you take this polymer chains in this membrane, if you take this polymer chain membrane, there is a fully hydroxyl groups are there. So negatively. I just given hydroxyl, but there are other functional groups also there that can be also negatively charged. So this is negatively charged. So advantage with this is that this through this membrane only positively charged molecule can penetrate. Because of this charge repulsion, it won't allow negatively charged ions. It won't allow negatively charged ions. It will allow only positively, because this is negative ion exchange, anionic membrane, that is negatively charged membrane. It will allow only Na plus ions to pass through. It won't allow Cl minus ions to penetrate through. So that is the advantage. Upon developing these ion exchange membranes, most of these NaCl saltwater electrolysis, NaCl electrolysis is made of from the membrane process only. So if you just see here how this works. This concentrated NaCl, the concentrated or saturated NaCl is feed, and when you feed this one, you can see Na plus ions and chlor. You can see here when you feed this concentrated NaCl, Na plus ions, Cl minus ions both enters into this anode side, and upon entering, this chlorine minus ions migrates towards the anode, and these two chlorine minus ions combine together and formed as a chlorine gas. These Na ions which are present here, which has tendency to move towards cathode because this is negatively charged, and these are the positive ions. And since this is an anionic membrane, that will allow Na plus ions to move through. That will allow Na plus ions to move through. So Na plus ions are moving. Na pluses are migrated towards the cathode through this anionic exchange membranes. And two chlorine ions, Cl to Cl, and joined together forms as a chlorine gas. So here, whatever Na plus ions coming here and here, with the help of this electrons receiving from the anode side, this oxidation of H2 is happening. So here, hydrogen OH, they'll break down to OH minus ions and Na plus ions. They join together and forms the NaOH. That way, and whatever hydrogen is formed here, that will be taken out. So with the help of this membrane electrolysis process, we're able to get NaOH, we're able to get chlorine gas, and we're able to get hydrogen gas from the salt solution. The same thing is depicted in this picture with what concentrations we are getting and what quantities we are getting. In an industrial scale membrane electrolysis process, this type of electrolytic cells will be used. So there will be many electrolyte cells are stacked together. Like you can see, this is one. So this is one, and this is two. Like this, many of them will be stacked because they'll be small, because whatever liquid which is surrounding the electrodes, they will be reduced and oxidized. So that's why very small, very thin, to enhance that surface area, there will be many modules. Many modules are joined together. And here you can see there is a pipeline. These are the pipelines. This is one, this is pipeline 2, and these are the pipeline 3. Through this pipeline is connected to each unit. Through this, through one pipeline, brine solution will be going, and to another pipe, we take out the concentrated brine solution. You can see here. This is the typical, let's say, 1 unit. If you take any 1 unit from here, that looks like this. Within this 1 unit, you will have an anode and you will have cathode. And here, from the pipeline, here you see from the pipeline, through one pipeline. See, this is one pipeline, and this is another pipeline. This is the another pipeline. This is another pipeline. One pipeline is used to introduce sodium chloride solution, used to introduce sodium chloride solution. Another pipeline is used to introduce water or very dilute NaOH. Very dilute NaOH. So exactly what I've explained before, and this is separated by a ion exchange membrane, anionic membrane, negatively charged membrane. So here same whatever explaining, at anode Cl2 forms, at cathode hydrogen forms and OH minus ions, and they will be, so whatever concentrated by in solution will be taken out using one pipeline. I should put red mark here. The concentrated brine solution is taken using one pipeline, and here the concentrated NaOH will be taken through the another pipeline. So like this small pipeline which is connected to each cell, and that way one pipeline for NaCl, one pipeline NaOH, one pipeline for diluted brine, another pipeline for concentrated NaOH. That way, this type of a stacked electrochemical cells will be used in the commercial scale. This is only one cell. In a typical industry, will have many such type of electrochemical cells. Electrolytic cells are used for this production of chlorine gas and NaOH from the brine solution. So this is the industry flow diagram. This is actually I've taken industry flow diagram from an industry, and this is the source which I took in here. This is a company in Dubai. So they take raw salt, and they'll make through the salt handling process, they will produce brine saturator. Like they wanted to produce a saturated brine solution. These membranes are very ion selective membranes. So if you use excess than the saturated solution, you know, when you use the concentration is higher than saturated concentration, there's always formation of nucleation and the crystallization. So the salt crystals can easily affect this electrolytic membrane. So that's why they'll be very particular to make sure that the brine will get this saturated condition. After this, it will be sent to the primary brine, where they will do the whether any settling, any crystal, any mud formation, anything will be removed. So that way for the mud filter, because the brine quality completely depends upon the membrane which is used here. So that's why some preliminary primary treatments was used to make sure we get a good quality of the brine. So further brine polishing filter to remove any impurities. If you have any other ions, because there is a possibility of the other ions like magnesium and other thing. So they will use ion exchange column, simple ion exchange column to attract other ions. So that way they will get a purified saturated brine solution is introduced here. And after the electrolysis process, as we have seen, as I shown, explained before, you will get chlorine gas. So this is the chlorine gas come from here, and here the chlorine gases will be hot condition because we are heating it with the external power supply. So it goes to the chlorine cooling. The chlorine gas is cooled before it's sent out. Then we have the catholyte handling, where you get the hydrogen gas. One is coming from the catholyte, and that hydrogen gas also will be hot, and it goes to the cooling. Often they will use this hydrogen gas for the HCl synthesis, and here whatever NaOH is coming here, whatever NaOH is coming, this goes to the product cooling. Then often the caustic soda or NaOH which is produced here, it is 32% concentrated. So sometimes they will store certain amount of caustic directly as a buffer storage, and something will be concentrated, then converted to the flakes, converted to the particles. So that way, this is a simple process made from the salt water to produce NaOH and the chlorine gas. Often some amount of HCl is also introduced along with the brine. Often some amount of some amount of HCl is also introduced with the brine solution. The reason for introducing the HCl with the brine solution is if any like they will whatever dilute whatever dilute salt solution come from here salt solution come from here. If you add HCl to that one, uh, if you add HCl to that one, you can further enhance the, or if any Na plus ions which is not migrated to the, before you stop the process, whatever Na plus ions which is present here, that can cause the instability. So before the salt solution is taken out, they will mix with HCl. That HCl make sure that whatever Na plus ions are there, that will be combined and forms the proper NaCl solution. So this is all about chlorine and NaOH production from the brine solution. Chlorine and NaOH production from the brine solution. If you have any questions on this topic, you may please ask. Yeah, one important information that next week, as the examination week, as per the academic calendar, so I'll be conducting test on next Wednesday for 50 marks. Sorry, 40 marks. Next Wednesday, I'll be conducting test between 8 to 10 a.m. and the total marks of the test will be 40 marks. Total marks of the test will be 40 marks. And I'll be posting an assignment which I'll give 2 weeks time for you to submit. That is 1 week after the examination week. So that will be also included as part of my assessment, the test and the assignment. I initially thought I should not consider the attendance, but considering the number of people attending the classes or showing interest, I wanted to give some bonus marks for the people who are attending regularly for these classes, regardless of whatever the time. Of course, others they won't lose, but those who are attending regularly, they will get some bonus marks. If they don't perform in the tests or if they don't able to submit in the assignments, they will definitely gain marks with help of this attendance. So overall, if somebody is even now I'm not putting a constraint that they should attend, because considering this online scenario, health conditions, internet troubles, there are so many troubles which we face in this current time. So I'm not very picky, but those who are regularly attending, I see some of the students every week, even regardless Wednesday morning they join. I don't want to mention the names, but I know it because I see. So they definitely get bonus marks if even if they don't perform well or some less marks in the test, so they will be added. So that's what I announce. So again repeating, next Wednesday between 8 to 10 you will have a test which will contain 40 marks. So it will be, the test procedure will be 1 mark questions. So either multiple choice or one word answers, or at best you would have to write one sentence. So those are the answers. So I'm just thinking whether I didn't explore whether I should conduct through Moodles or MS Teams. So I will let you know once I get the proper clarity. I have requested Moodles teams to enroll the students, but they haven't done till now. So I hope they will do it. I will try to ask them again. If they enroll it, then I'll conduct tests through the Moodles. If not, we will always have the MS Teams. Because this is a 40 marks or 40 bits, it will be a little longer. It's easy or it is more good if conduct to the Moodle where less chance of where I can prepare a question bank from that randomly it will fetch questions to the each student. That is what I am thinking, but I'm not sure. If Moodle they don't assist me or help me, then I will conduct through MS Teams. So, if you have any questions on the test announcement, you may ask. Otherwise, we can proceed. I hope you're able to understand. You heard. Can anyone confirm?
Yes.
Okay. So test next Wednesday. Please prepare because I'm only conducting only one test as mentioned in the as students opined, few people at least. So I'm conducting only one test, and it is the major test. So please prepare. Is it very boring, the class? Okay. So next I would like to discuss cement production. Cement production is the, we can say, of all industries, this is kind of very simple process, cement production process. Although there are a lot of developments can still be done in this process, and it is very age old process. At the first, as I said, the first plant constructed after the independence is pulp and paper. After that, we have the cement production plants. So I'm sure you know some of the basic chemistry you might have learned in your plus two, but uh, let's go through this one. There are varieties of cements. The most commonly used for the household construction work or building construction is Portland cement. Portland cement. So, what is the nature of cement? What is the quality of the cement? Is that cement has a specific characteristics of hydration. Upon hydration, it will get hardened. That is the characteristics of cement. As you water it, it will become harder and harder. As you water it, it will become harder and harder. Up to a certain extent, of course. So that is the characteristics of cement. The hardening with hydration. We can say simple words. It is, if you want to put a simple word, hardening with the hydration. It will absorb moisture, and then whatever moisture it will absorb, that will use for the hardening by liberating certain amount of heat. By liberating certain amount of heat. So what the cement contains? Cement, Portland cement, the common cement used for the household or building construction work is this one. It predominantly contain three components. Predominantly contain three components. You can see major percentage. So C2S, C2S, dicalcium silicates, 2CaO.SiO2. Another one is tricalcium silicates, 3CaO.SiO2. And along with silicates, another important ingredient in the Portland cement is aluminates, tricalcium aluminates, 3CaO dot Al2O3. And often for the aluminate, we will add clays as a source of aluminate. We will add a clay, so that will contain other impurities like Fe2O3 or MgO or CaO. So we will have minor amount of formation of Ca, Ca4F, terra calcium aluminate, whatever big name. So 4CaO dot Al2O3 into dot Fe2O3. This is the minor person. If no impurity of the Fe2O3, sometimes it may not be present also. Based on the impurities, you will have MgO and CaO. But these are the predominant. So this is one type of cement. Another type of cement is high alumina cement. High alumina cement, since the cement name itself it says alumina, the predominant quantity is C3A. Predominant quantity is C3A. C3A, therefore, tricalcium aluminates, 3CaO dot Al2O3. Depends upon the impurities. You will have small amounts of silicates. And of course, hydrated lime, calcium hydroxide. Hydrated lime is predominantly calcium hydroxide. This is only used for as a brick mortars. This is only used for the brick mortars or also white cements. This is typical white cement, hydraulic hydrated lime. The Portland cement used for the, as I said, common building construction. High alumina, I think I will have, if you explain this, you will understand better. What is this? Dicalcium silicates? What the role is that? When you hydrate it, it immediately hardens. Dicalcium silicates, as soon as you water it, early strength. It hydrates, gives some strength. Oh, I think I have written a mistake here. Sorry. This is tricalcium silicates gives the early strength. This gives the later strength. After few days, after if you repeatedly hydrate it, if repeatedly pour water, that'll get hardened. So later strength. So if you add water to the calcium silicate, immediately as soon as you add water, it'll get hardened. So if I take cement which contains only C3S in 3 days, it will become hardened. But the relative strength is little lower. If you have only C2S in the cement, it won't get hardened immediately. It will take a lot of time to get hardened after the hydration. Now, why is this aluminate is required? Is that, if it is fully soaked, let's say cement is fully soaked, it will never get hardened. Whenever you want to enhance the bonding between something, some amount of heating has to be there. So this calcium aluminates, upon hydrated, it generates high amounts of heat. There is typo here. High amounts of heat. It will release a lot of heat. That whatever heat released from these, that will basically does the sintering effect near the silicates and other ions. And this one is to get the dark color, C4AF, to get the dark color. So because of this, typical Portland cement contain 40 to 60% of C3S. 40 to 60% of C3S. This is the early strength. This is the later strength, and this is the to liberate heat upon the hydration. So that's why, as soon as you in your household construction, as soon as you apply, you will see in a few hours, not even few hours, it will get strengthened, it will get hardened. But to get a full strengthening, full effect of all these three, C3S, C2S, it will take almost 28 days. That's why the buildings, when they constructed, they will say you need to do regular watering. Those buildings which are not done regular watering, they will not be reached the full strength, and you will get a cracks. You will see cracks in the wall very fast because of this C3S and C2S relative contribution. Of course, there are many grades. I just only gave the composition of regular grade cement. There are high grades, low grades, depends upon the ratios of this. Early, if you wanted a quick hydration, a quick strengthening, they will increase C3S. If you want a later strengthening, they will get C2S. But the later strengthening is always good. Why? As slow it builds the strength, that protects for longer and longer time. People says some of the age-old constructions like forts and big museums which are very old, they made of predominantly C2S. Although it took time to hydrate it, but that strengthening effect lasts for very longer time, very longer time. Now, high alumina cement, as I said, it contains predominantly C3A, predominantly C3. High alumina content predominantly contains C3A, and some amount of C2S or C2S will be there. This is used for what purpose? If you want to use cement for the subsea construction or underwater construction, they use this high alumina cement because rapid rate of strength development, rapid rate of it quickly develops strength and hardens very fast. It doesn't need any time because of the high rate of heat liberation, and also superior resistance to seawater and the sulfate waters. So high alumina cement used for the underwater constructions or subsea constructions. Now there's another type of cement which is only magnesium oxychloride. Like if you sinter the magnesium oxide at high temperature, you will get this magnesium oxychloride. So this will be spark proof. If you use the cement, it will be spark proof and wear resistance and high bonding strength to wood fibers. High bonding strength to the wood fibers. If you most of the house construction in the foreign countries like European countries and Australia, even US, made of the wood only. They make the house with help of the wood only. They won't use like what we do here. Is that we use bricks to make the walls and everything, but they use only wood, timber only to make the what major amount of the construction work. But the wood alone doesn't protect from the weather conditions, so they will stick some bricks. They will stick some bricks with the wood fibers, whatever wood. So for those, they cannot use Portland cement. That won't work for them. So for such cases, they will use magnesium oxychloride. What I meant to say, I'm sure you guys would have explored. I lived in Australia for a long time, so I know. So house construction, the Australia, if I see images, yeah, you can see they will put they will foundation as we do. They also do the foundation, and I think this is the right image. You can see they will make the whole structure like we make structure with bricks, but they make whole structure with the wood frame. Then they will stick the bricks. Then they will stick the bricks to the wood frame. You can see this is the ply, and you can see this is the ply. This is the ply. So this is the wood, and this is the wood framing. And you can see they will what you say. So this is the ply, and on the top of the ply, they will see this is the whole house frame, and they will put a ply here. Then they will put some foam for the insulation purpose. Then they will put another ply, then they will stick this bricks. See, these are the bricks, they stick it. If you want to do such thing, if I want to use high aluminum cement or Portland cement, doesn't work. There you have to use the magnesium oxide chloride cements for, because the bonding strength between those with wood fibers are very high. So I have only shown 3, but there are almost 11 types of cements are there. So how do we produce this cement? So we have, or across the world, every country has this limestone reserves. Limestone reserves. So I think mistakenly we can use iron ore, or we can also use clay. I only kept one. I forgot to keep. We can use clay, which is contains Al2O3 and Fe2O3. Iron also contains Fe2O3 and Al2O3. Of course, the composition changes. So clay can be used, iron ore can be used, but predominantly clay uses, most of the industries uses the clay. So the key reaction is that limestone and iron ore combine and heat it high temperature greater than 1000 degrees centigrade. 1000 degrees centigrade. What we produce, just sintering. If you take limestone, mix some clay and sand, then heat it at high temperature, then what you produce called clinker. What you produce called clinker. Clinker is a mixture of C3S, C2S, and C3A, and few other components. Depends upon the impurities which is present here. Depends upon the impurities which are present there. So, what reactions happen? Limestone predominantly contains calcium carbonate. Limestone predominantly contain calcium carbonate. When you heat the calcium carbonate at high temperature, that breaks down to CO and CO2. CO and CO2. That CaO reacts with Al2O3 and SiO2, then forms this mixture of C3S, C2S, and C3A, which is also known as clinker. So two solids, limestone is solid, iron is solid, and you are heating and producing another solid. So this is the typical reaction where the raw materials are solids, the raw materials are solid, and we won't often see such thing in our chemical engineering processes. So although reaction is happening, but it is solid to solid interaction, just heating only, just heating only. Although there is a reaction, but we don't need any separate reactors. We don't need any separate reactors. Simple solid heating instrument is sufficient. Solids heating is sufficient. Any guess from the students? What are the instrument, or what are the equipment we use to heat solids, to dry the solids, to heat the solids? I already explained which is used for the drying of the solids, which is inclined. Any guess from any student who present today? What the equipment name we call it? I will hint. It will start with K. I explained earlier. Maybe you could not recollect. That is called kiln, rotary kiln, rotary dryer, or rotary kiln. Both are called rotary dryer, which is also called as kiln. So that simple heating, rotary kiln is sufficient for this clinker formation from the limestone and the clay or iron ore materials. So here, this is the typical process. These are the limestone rocks, limestone reserves. It is available at few places in our country, Gujarat and few other places. So this limestone rock is very hard. The limestone rock is very hard. It is not easy to crush it just by the any type of normal instruments. So what they do is they do the quarrying, that is blasting. So wherever limestone rock is there, they will blast it. Upon blasting, you will get a fine, like small, big chunks of rocks, big chunks of the limestone rocks which are produced here. Big chunks of the limestone rocks are produced. Now, these big chunks of the limestone will be crushed using this type of the jack crusher. This is a typical jack crusher, impact crusher. You can see this is an impact crusher. So we have impact head and there is a moving head, and when the big particles come here, they'll be crushing between this point, and they'll be also crushing between this point, and further whatever particles which is going will be further crushed at this point. 3 points, one this point, one this point, one this point, all the three places, the impact crushing, impact between the two, one stationary, one moving, strong bars, iron bars will be there. So impacting between these two will be helpful to crush this big chunks. So this is the typical impact crusher. So the crushing can only reduce these big chunks to the particles of few millimeters, but it cannot reduce to the fine particles. Like in micron range, it will not bring to the micron range. Crushers cannot bring to the micron range. To bring down the particle size to the very fine size, you will do the ball milling. They do the ball milling. I'm sure you learned this ball milling in the mechanical operations course. We have a cylindrical vessel which is filled with balls, These are the hard iron balls. Then you will add the material which needs to be the grinded. You will add material which needs to be the grinded. When this ball rotates, when this ball mill rotates, what will happen? These balls also rotate, and the balls tend to move up. The balls tend to move up and falls down. The balls will tend to move along with the ball mill and tend to fall down. When ball falls over another ball, falls over another ball, impact or crushing impact between or attrition between two balls will takes place, and whatever material is there between those two balls will be converted into fine particles. So typical ball mill used for the cement production process, you can see, is a huge ball mill. And here I just kept a video just to show how this typical right. So huge ball mill. Yeah, you can see here. This is a huge ball mill, which is continuously rotated at a set amount of RPM. So this is the typical from the top view, whatever the ball mill which is continuously rotating. And here this is the gearbox of the ball mill, and this is connected to the big motor that rotates the whole ball mill, and the corresponding corresponding ducts to separate the any fumes which is formed here. And you can see whatever fumes which is formed goes here and collected and separated with help of the centrifuge cyclone separator. So, right. So that ball milling, often they crust it to such that often this crust it to such that will passes through, or it will be almost like a 75 micron size, almost like a 75 or smaller than that 75 micron size. So it almost gets from big rocks to big chunks of rocks to almost fine particles of almost 0. Or 75 microns. 75 micron size particles are brick crust. It will reduce to 75 microns after the ball milling process. So here, this limestone, which is crusted very fine particle. So 70% of this limestone mixes with clay, which contains Al2O3. Then the sand, because some limestones base depends upon the purity of the calcium limestone. If the purity is very high, it doesn't have any SiO2. If it's low pure one, it will have SiO2. So it depends upon the purity. Sometimes they will add sand, sometimes they will not add sand. So assume that this is less amount of SiO2 is present in the limestone. So they're mixing the sand and fly ash. Fly ash actually not needed for the cement production process, but fly ash is the slag, the byproduct come from either steel plant or many other industries. So just to reduce the cost of the cement, and it also has this hardening upon hydration capacity. They will add little amount of fly ash to reduce the cost of the process, to reduce the cost of the production process. They'll add fly ash, but all in theory we don't need fly ash to be added, but just to mitigate the cost, they add this fly ash or slag from other industries. So all the three are mixed. All the three are mixed. So here they use called vibrating mixers, VRM. Just want to show you vibrating mixers, vibrating grinders. Where is that? Yesterday I had a good video. Okay, leave that. So they grind it. Basically, this grinding is only for mixing in a homogeneous way. Mixing in a homogeneous way. I think next picture is better. So we have limestone rock crushed into small. Then they will add sand and clay. They will add sand and clay to this one in a proportionate instrument. Then uniform mixing of limestone, sand and clay, and uniform grinding will be taking place. After that, it goes to the preheater tower. After that, it goes to the preheater tower. So whatever material we need to heat higher than 1000 degrees centigrade. We need to heat higher than 1000 degrees centigrade. Since we cannot heat that high temperature immediately, they will have some preheater. So in the preheater, this is the whatever boiler waste heat, the boiler waste heat coming from the boiler waste heat, which is utilized for the preheating these all the three solids which is mixed here. Preheating all the three. You can see this whatever white color or bright color, that will be limestone and sand, brown color. So all the mix they preheated. So preheated to certain temperature. Then it will be introduced to the kiln. Then it will be introduced to the kiln. Kiln is nothing but a simple cylindrical drum Kiln is nothing but a simple cylindrical drum, a rotating cylindrical drum. Rotating. Why are we rotating? For the uniform mixing of the solids. For the uniform mixing of the solids. So this is a cylindrical drum, and which rotates continuously, and the particles are fed from the top. The particles are fed from the top. From the bottom, from the bottom, they have to introduce hot air. They have to introduce hot air. This hot air should be very high temperature so that these solids can be heated up to temperature higher than 1000 degrees centigrade. So how do you heat it? They will inject fuel. They will inject fuel. They will inject hydrocarbon fuel, and they will introduce air, and they'll burn it. They'll burn it, just like internal combustion engine. So they will use the high pressure fuel, and they'll burn it. So upon burning the fuel, you will get the gases that will create a lot of heat. That heat will be utilized for the that heat, whatever heat produced with help of the fuel and air combustion, will be utilized for the heating of the particles to temperatures higher than 1000 degrees centigrade. So here I have a picture or video that can show a typical kiln, industrial kiln, how it looks like. So this is my government Ministry of Steel created a video. So this is the this is the typical kiln looks like this. This is the typical kiln, like a big cylindrical drum, which continuously rotates. The speed will be 2 to 10 rpm. So the typical kiln will have a blowers, will have a blowers to inject air at intermediate points. They have the blowers introduce the air at different points. They also have the fuel injection systems at the different points so that the fuel will be burnt and generates heat at high temperature, and that will be utilized for the heating of the particles which is present here. Rotary kiln present in many industries, so yeah, you will be able to definitely see if you just Google it. So this is the typical animated video of the kiln. The solids are fed, and this is the inclined shape so that it will be the solids will move by the gravity. As it moves, this will rotate. As it moves, that will rotate. During rotation, solids are circulated or mixed. That way, you will get the mixing of the solids by sending the gases hot air from the other side in a countercurrent way. The hot air comes and gets heated, and centric effort can be takes place. You can see here this way it rotates continuously, and you have the intermediate blowers is placed to introduce the air at different levels. Shell air fans, and we have thermocouples, that is one. And here it given a glimpse of burning of the fuel, so I thought to show you. So this is another rotary kiln. Yeah, here you can see how the hot air, how the fuel is burnt, in this, and sent at the very high temperature, because we need almost 1000 degrees centigrade higher. This hot air with the fuel injection system is introduced, just to show that. Rest is similar what I just showed in the other. Here you can see skin, and how this video explains how the kiln moves and rotates, and how the gearbox looks like. You see, this is the gearbox, and how this gearbox helps to rotate the kiln, and this is the belt. So all rest of the thing, motor, everything this video explains. Of course, if you're interested, you can see later. Anyway, keep this YouTube links here. Yeah. So upon heating this clay, limestone, and sand mixer, what produces is called clinker. What produces is called clinker. Clinker is basically C3S, C2S, C3A, and other components, depends upon the impurities which is present here. So since it is very high temperature, since the clinker comes in very high temperature, that needs to be cooled. That needs to be cooled. So they will use cold air to cool this one. You know, when you introduce cold air or whatever water to cool this one, it'll generate steam at high temperature, or it will generate air at high temperature. So that hot steam or hot air will be sent back to this preheater to heat these solids before it enters the kiln. Before it enters the kiln. That way, this waste heat, the heat from this clinker cooler, the heat from the heat recovery from the clinker cooler, or the heat removed during the clinker cooling, will be utilized for the preheating. Will be utilized for the preheating. That way, it minimizes the net amount of heat requirement. That minimizes the net amount of heat requirement. So here, after cooling, they also add, as I showed, here they didn't add gypsum or fly ash. So they add fly ash or gypsum or any slag, depends upon the industry's availability nearby. They will add some amount here just to mitigate the cost, because gypsum is available almost low cost, almost free of cost. So that gypsum will be mixed to reduce the cost of the cement. Since we are adding something, we need to grind it and we need to mix it. We need to do grind it and mix it whenever we add some two solids. So just simple grinding and mixing equipment will be done, and it goes to the storage where silos will be there, and that will be the stored and the shipped. That will be stored and the shipped. So this is the way cement production is done, and which is very simple process. Everything is typical unit operations which we discussed in mechanical operation. All the things here except the clinker cooler and the preheater, everything is simply what we taught you in the mechanical operations course only. Crushing, grinding, silos, mixing, and kiln. All these things are very simple processes. Simple uh, process. Yeah. So this is about cement production process. If any student have any questions, please you may ask me on this topic before I move on to the next one. Okay, if no questions, I will just take some water. Then I will start the discussion after 4 to 5 minutes. Please be available online. So I'll just take some water, and after 4 to 5 minutes, I will continue the discussion. You may also drink some water or use washroom, whatever.
Yeah, good morning again, students. Thank you for waiting. So, next 15 minutes, I wanted to give a quick overview of pharmaceutical production. Although it is a huge subject and you will learn more details in your biochemical engineering course. So, I wanted to limit the discussion more in terms of the process flow sheet. So, let me share my screen. What happened? And come on. Yeah, now ready. So here, any just take an example of tablets, pharmaceutical tablets. Any pharmaceutical tablet you take, they'll contain two ingredients. One is called active pharmaceutical ingredient, which is also commonly known as API or abbreviated as API, active pharmaceutical ingredients. Another one is called excipients. Another one is called excipients. So, so this active pharmaceutical ingredients, it has the therapeutic effect. Basically, what is the drug substance that treat that specific disease condition? That will be the drug substance. It must be present in a specific concentration in a dose, a specific concentration. But often that specific concentration will be very, very low in few milligrams. Very, very low. It will be few milligrams. So the drug, which is basically cures the whatever disease or whatever, that has to be maintained in a specific concentration. It cannot be high, it cannot be low. But even that specific concentration will be always very, very low. That will be always in milligrams. And it is very hard to very hard to handle 20 milligrams of a substance in a solid form and sell it. So for that reason, for that reason, they they add excipients, which are the support what yeah which give the support material, which give the support or handling of that mass. So excipients doesn't have any therapeutic effects. They're necessary to provide desired properties like size, shape, color, resolution, and hardness, etc. The active pharmaceutical ingredients often doesn't have mechanical strength upon drying, and it's also always in very, very small quantities. and you cannot convert them into a crystal of a specific shape or whatever. To give a specific size, specific shape, specific color, specific strength, specific dissolution characteristics, they mix this active pharmaceutical ingredient API with excipients so that you will get a tablet of specific shape, tablet with a specific dissolution rate, tablet with specific hardness. Because the final solid product what you make, that should be strong enough to survive the handling and transportation. At the same time, it be fragile enough to dissolve at a desired rate. Once you consume the tablet, that should be fragile enough to dissolve at a desired rate. These are the two important characteristics. It should be mechanically strong, at the same time fragile enough to dissolve at a desired rate. Because 80% of all drugs is actually sold right now is of tablet form. Is of tablet form. So, so this is the uh, one example: aspirin, aspirin tablet for a quick pain relief. Aspirin is the very commonly used pain relief medicine. So in the aspirin, this is the active pharmaceutical ingredient, acetyl salicylic acid. And what is the quantity amount of the this API used in the aspirin tablet? It's only 300 milligrams. 300 milligrams per one tablet. So if you take, let's say you just want to supply this acetyl salicylic acid only, it is not possible to put it as a solid form in a specific shape, specific manner with a specific dissolution characteristics. It's not possible. So we'll add excipients like cornstarch or certain kind of wax, and sometimes they also use powdered cellulose. These are the excipients. The excipient is not only one; it's a mixture of many things because you need to get strength to handle it during the transportation, whatever, and you should be present enough to dissolve at specific rate. So they will add wide variety of excipients, and here we have listed few of these excipients here. And here they wanted quick, the dissolution rate should be very fast because it should dissolve very fast, and that should be absorbed in our blood very fast so that we can get a quick pain relief. So here one of the example of the active pharmaceutical ingredient. Oh. So I just took one example, which is paracetamol. So paracetamol is, we can produce using the simple reaction. I think it is there here. Yeah. So paracetamol is made from this simple reaction, or from this, not a simple reaction, from these molecules. So phenol and phenol converted to the para-orthonitrophenol. Phenol is converted to the para and orthonitrophenol. This para-nitrophenol reduced the aminophenol, and that is further converted to the paracetamol. So nitrophenol is the key source component for the paracetamol. So this is API is made from the simple reaction or typical reaction. Maybe I'm using this word simple, but from a typical reaction point of view. If they always try to prefer to produce enzymatic reactions, if it is not possible, then they will do the normal reactions. And here, very good, I have found, we have visited an industry where I have seen this type of process. So I think this will give you better. This is the typical batch reactor. This is the typical batch reactor, and you can see it's a huge reactor, almost like if you ever visited our department, one single floor height of that much will be there in one typical batch reactor. So here, this is the batch reactor with this specific temperature and pressure control. So they will feed the ingredients. See, they will feed this whatever required chemicals, and they will mix in the batch reactor continuously for the required amount of time. So once you get the required, the complete reaction is achieved, whatever solvents they added, whatever unwanted components they added, they will remove out. They will remove out, and whatever the final required amount of required chemical which is used as API, that will be separated, and that will be freeze dried. That will be freeze dried and converted to the solid particles. That will be freeze dried and converted to the solid particles. This API is the crystallized, the solid form of the API, the crystallized the solid form of the API sent and mixes with the excipients and mixes with the excipients here. After mixing the excipients and the active pharmaceutical ingredient, of course they will do the sampling time to time to see what concentration, and then they will do this tableting process. So here I have the flow sheet. So this API feeder and excipient feeder, both are blended together with help of a blender. So upon this uniform blending, they will do the granulation. They will do the granulation by adding certain amount of solvents, certain amount of solvents. Then they will crush it into the required form. Then they will do the tablet form. So I hope you have seen the punch discs. If at all you visited, if you have done any research work in a department, there are many labs which has the punch disc or DRF, Department of Research Facility. So how this punch disc looks like is very simple. So here we have a whatever shape, whatever size you want, you will have this is type of a metal made of this one with the required cylindrical shape. Then you will fill the powder. You will fill the powder up to the required height. Then this is the powder. This is the powder required height. Then they will cover with a piston. They will cover it with a piston. They will compact. They will apply certain amount of stress here. Then it will be get compacted. It will get compacted and form like a hard solid tablet form. Hard solid tablet form. So that is the tablet press. Very simple. API, excipients mixed together in a blender, then crushed into fine powder. Then they will add certain amount of solvents to give the proper consistency. Then it will be compacted in a tablet process. Then they will supply it as a tablet. So it is exactly similar. You will have a batch reactor in which you will get the active pharmaceutical ingredient is produced. Then that active pharmaceutical ingredient is crystallized and freeze dried. Then mixes with the excipients, and excipients and API are mixed together and crushed into fine powder, then compacted with help of the tableting machine. So there is one company called Novartis. Novartis recently conducted a workshop how to use this artificial intelligence and other techniques to enhance this process ability. Like I just previously I have also attended that workshop, and this is the presentation where how we can use this our chemical engineering knowledge and age old PCA, whatever principal component, else other component analysis to use this the whole process very good manner. So what I wanted to say is that even those who are aspiring for this AI or machine learning, whatever, major amount of technology is now moving towards chemical process industries, because in the chemical process industry, for example, if you take this flow sheet, there'll be always fluctuations of these what are the concentrations of this API conditions, the flow rate conditions, blending conditions, when there's a power failure, when no power failure, when excess power comes, how this mixing varies. There'll be a lot of data. That data can be modeled and used as a used can be used to enhance the process. But to that, we have to understand the chemical engineering. If without understanding chemical engineering, without understanding the blending process, without understanding this, you will not be able to use those techniques. Definitely, gaining knowledge here will be a helpful. Definitely, even in whatever aspirations you have. So, with that quick overview on this pharmaceutical production process, I will end here. If you got any questions, you can ask. If you have questions later, you can always message me. And with that, I thank you all and have a great day.
Sir, when would be the test for the this part?
This part means
Like for your part, because like next week is the test week. So
I just announced next Wednesday.
okay, sir. Yes.
Others heard or not? I've only Sai Vardhan is missed. Others heard of the test announcement. Can any other student confirm?
Yes.
Yeah, I actually between around 8:55, I think I have announced at the middle of class. I announced that test for my
Okay,
portion
sir.
will be next Wednesday. The test will be of 40 marks.
Sir, would it be on Teams or would it be on another platform?
I was trying to conduct in Moodle. I have requested them, but till now they haven't enrolled the students. If they do enroll, then I will conduct the Moodle. If that what doesn't work out, I will conduct two Teams.
Okay, sir.
Any other questions from any other students?
Thank you, sir.
Yeah, thank you all. Thank you so much.